students here with logistic growth problems. From what I understand, those of you guys that have had biology before, you've seen this. There's a point at which, I think it's the bacteria problems where you put them in, the bacteria grows in a petri dish at a specific rate. The rate increases, and then all of a sudden it tails off. That's logistic growth. There's a ceiling, there's a maximum value at which the amount of bacteria you can have in a dish. There's a maximum value that these things are going to approach before you run out of resources, if you will. It is a real world style problem that's pretty easy to work with. You don't write outside, I'm just kind of giving you a definition here. These growth functions are used to model real life quantities whose growth levels off because the rate of growth changes from an increasing growth rate to a decreasing growth rate. Basically, these curves look like this. These curves are going to look like that. But what happens is there's a floor and there's going to be a ceiling. You're going to have asymptotes. You'll have two asymptotes with these style graphs. One of the asymptotes will always be at 0. The other asymptote's going to be at some other value depending upon the function. Being horizontal means that they're always y equals value, so it's pretty easy to work with. There is the one change, the point of inflection, if you will. That's where the things are changing from your increasing growth rate to a decreasing growth rate. That's it. I don't remember what that thing's called. Point of inflection. Sure. But there's a whole lot of mumbo jumbo for the function itself. Don't freak out. Oh, it's called the point of maximum growth.
Oh my goodness.
It's not as cool. Think of it as a population boom. Okay?
I think it's the maximum growth point. Why do they always do point of whatever?
It's like Spanish, you always have to say like that.
The house.
Es posible. La puerta está ahí. La ventana es un reloj.
That's a Spanish
Mi accente es muy importante.
I have one of those.
So what I want you to think about here is a very easy model to comprehend. Population boom. When you talk about population boom, you think about specific parts of the country where growth took off. Recently, growth of population took off. I want to say Florida and Arizona. Those were the two states that had the highest population growth over recent years. It took off at the beginning of the 2000s, and it just grew rapidly. There were real estate developments going up all over the place. And then it started to tail off because the economy tanked. That's the kind of idea of what happens, where you still have a little bit of growth there, but yet it tailed itself off to a specific cap. You're going to cap out a population area if you think about, you can't wind up, I mean, India has like 17 billion people, right?
Yeah, probably not.
Not 17 billion, you know what I mean. There's a lot of people there. There's not a lot of room for anybody else. There's a certain cap on resource. You get the idea. Okay, so over-exaggerate by a couple of billion.
16 billion.
How many do they have?
1 billion.
1 billion, that's
I think
it?
they have a billion.
Yeah, I'm pretty sure they did.
Google that.
There's definitely a lot.
There's
India
maybe
now
close
has
to a
more.
billion, but that's like
There's a billion people in China.
Well, China's way bigger than that.
But like,
All right, hold on.
India
We have
has
1.25 billion.
Take that.
no, but like India has
Whatever.
And China has 1.357.
All right, so China, guys, China has 1.3 billion, and India was 1.25?
Yeah.
It's almost there. Exactly.
And we have 316.5 million.
So here's what all of this boils out to look like. All of these graphs, they're relatively easy to work with, though. All of these graphs and of this function fit this model. I'll write some of this out.
Wait, can it ever be in the fourth quadrant, or is it always in the first?
It was so bad.
It's going to be always greater than 0. So it's always going to tail.
But like it can go down, right? Or does it always?
No, it's, you have a ceiling at 0. So every
Yeah, but no, I mean like.
Oh, it can be first, second.
Like, can it go like this, or does it always have to go down?
I think it's always going up and right. Yeah, it's always increasing from left to right.
So it's never going down?
Correct. Wow. Anyway, so you get this junk, and as you pull the stuff out of this, what's happening here is that it allows you to graph the stuff out. So I'm going to look at the example I have there is y equals 6, 1 plus 2e to the negative 0.5x. I'm going to use that to show you how you pull those pieces out to graph it. And I'm just going to graph it on the whiteboard here. We know that you have a horizontal asymptote at y equals 0. There's always one there. And the other one's going to be at your value of c. The value of c is your numerator. So what's your numerator? 6. So you have another asymptote up at 6. So all that's going to happen between here and here. Okay? The y-intercept is just the numerator divided by 1 plus a. Now your value of a is just the coefficient that's in front of the e. So my y-intercept is going to be 6 divided by 1 plus 2, which is 2. Okay? So y-intercept at 2. I know that the domain of all possible x values can occur. It's increasing from left to right, so I know that it's coming this way, and it's coming up to here. That's really all there is. The only other point that you get is that maximum growth point. That maximum growth point occurs at the natural log of whatever your a value is divided by r, comma, c divided by 2. Okay? So what you're looking at here is your a value is 2. So you get the natural log of 2. Your rate in this case, which is what?
0.5.
Negative.
Wait,
Wait, I thought it was negative R.
it says negative r.
Oh, yes, I'm sorry. Thank you. Yeah, so it's 0.5.
So it's 1.39.
Whatever that decimal is? Yeah, whatever it is. And then that's your x value. Your y value is just your numerator divided by 2. 6 divided by 2. So, Colin, you told me what this was?
1.39.
1.39. And I could probably figure out 6 divided by 2.
4. All right.
So now that means at, here's 1, here's 2, 1.39 and 3, there's our maximum growth.
What about minimum? Is there a minimum?
No, because there's no floor. You have a minimum value at an asymptote of y equals 0.
Okay.
All right? But that's the maximum growth rate is right there. That's it. Those are the 2 points you find. It's just a matter of getting used to a couple of these values, okay? As you build out of it, it's not a very complex scenario.
I think so, but I was going to say so.
And then,
She's grading 7, 8 first, so.
so then max growth, natural log of
Did you
A
guys do you
over
she-
R,
first last time?
and then
Yeah.
C
Yeah, you guys are last this time.
over 2. Let's try another one.
How much harder is this?
There's really not much more to it. It's just a matter of graphing it. When we do the actual modeling itself, You're still going to look at your table. You're still going to plot the graph to tell if it's going to be a logistics style versus a, while this has the change of direction, it might kind of look like a cubic function. But I'm going to show you the difference between this and the cubic is very, very obvious when you look at your tables, because there's asymptotes. That's how you tell if it's not cubic. Okay? That's how you tell. So we start again by, the easiest thing to do is plot your asymptotes.
Wait, where's E?
Remember it's e to the x. It's exponential.
Oh,
E, the inverse of e is natural log.
oh, right.
So we know we have an asymptote at 0, y equals 0, so we put that one in. Where's my other asymptote? 4. My other asymptote is at y equals 4. I know that my y-intercept is going to be at 1, because it's 4 divided by 1 plus 3. It's convenient how you can just do that and figure it out, right?
Yeah.
That's great.
Wow. And then, oh man. So then it's the natural log of a over, what is it, r, and then c over 2. Your a value is 3, so it's the natural log of 3. Your r value is 3, and then it's 4 divided by 2. So whatever the decimal value works out to be, there's your other point.
0.36
0.36 and 2.
and 2.
Wait, shouldn't be 0.36. Shouldn't it be more than 1?
No, it's
Let me look
Zero
at
divided
this.
by 3.
Hey, not,
The
it's
natural log and
point,
then divide it by 3.
divided by 3.
0.37.
it's point three six,
Well, it's
it's
0.37.
point 0.37 if you round up. Yeah. Here, you give it the program. First.
Always be.
That, but then it puts it, oh, duh. So it's here. Okay, so it's like, it's mirrored out. It's really close to the minus because it's coming up and doing this.
Is it
It's at 2.
Oh, 2.
No, the 2. 2's the line.
0.36.
Oh, I'm an idiot. I'm sorry, I was reading it backwards. Y is an X is high. Good morning.
Hello.
I was wondering, like, why is this?
Oh, no, we switched to accent.
And there's
Done
your.
that for a long time.
I know. I deserved that one. I'm just not very good at math. Okay.
Amy, you can check my grade.
All right. All right. Let's see if you can do this one then. Solve for x.
Solve for x.
Solve for x. Let's see if you remember how to do that.
I knew this was gonna be hard.
I'm not even going to show you.
Wait,
Solve for x.
so the x, like the negative 3x? Or
Yeah, I want you to solve for the x that happens to be right there.
Alright.
Solve the equation.
First, you
Run through it real quick.
I was gonna
Does everybody agree that this is 40 over 1?
Yeah.
Yeah.
So is that fraction equal fraction?
Oh, man.
Ah, duh.
Oh, poop is right. So I get 50 equals 40 times 1 plus 10 e to the negative 3x divide by 40.
Oh.
5, 4.
That's a lot smarter.
See, I did it the other way. I mean, I just like did it where you,
Wait, isn't it
To
40?
fraction one.
okay.
So 1, 4 equals
So now I have 5/4 minus 1 is 10 e to the negative 3x. Okay with that? What's 5/4 minus 1?
1/4.
Can I write 0.25?
Yeah.
Can I divide that by 10?
Yeah.
And have that?
Yeah.
How do you undo an e?
Log. Your natural log.
natural log it. So you get the natural log of 0.25 over 10.
Pretty sure there's more than 4 steps, you're saying.
4, 5, 6, whatever.
Negative 0.3 or 3.69.
Whoa.
So all in all, you wind up having to do
Wait, what?
That divided by negative 3.
Okay, so
1.22.
1.23.
2.3. My bad.
I understood this about like 4 steps ago.
1.23?
Yeah.
I
There you
mean,
go.
yeah, that's
Can you scroll back up?
Wait, why did you do that?
This makes so much sense.
All right, once again,
Are you being sarcastic?
no, not at all. Here's what happens.
Oh, I get it.
What I want you to notice right off the bat is since you have it equaling 40, 40 is the same thing as 40 over 1. That means I can exchange across the diagonals. So all I do is just flip-flop on the diagonal here. These two guys switched. I get this. 50 over 40 is 5 over 4. From there, I move the 1. This was an easy fraction to switch to a decimal because we could do that in our head. That's why I wrote it as a $1.25 minus a buck was a quarter, 0.25. At this point, we had 0.25 was 10 e to the junk, divided by 10. I could have rewritten that out as a separate decimal, but it doesn't make that big of a deal because I'm going to use my calculator eventually anyway. So I left it like that. So I had a 0.25 divided by 10 was e to the negative 3x. To get that negative 3x to drop down, I have to undo e. When you undo e, you natural log. Natural log divided by negative 3, that's how you got it. So yes, there was more than 4 steps, but they should not have been difficult. Miss Erin,
So what if you can't change the fraction into the decimal?
then just use your calculator. That's it. I mean, you use your calculator and go through all of it. I mean, to be honest with you, as you get to this part here, you could do all of that in your calculator if you knew the steps. By the time you do 2 of these, you'll be like, oh,
Yeah, you're right.
we're running a little short here, but I want to talk a little bit about how we use logistic regression when you're dealing with a word problem and tables. So instead of having you guys try to write all this out, I ran it off and hole punched it.
You're saying,
I tried. That way you guys can have it and we can kind of work through it real quick.
I didn't, you never said.
Hey, Jared.
I'll catch up in that next year.
Yeah.
Oh, dude, what's that? I'll take
Why?
I talked to him yesterday, he was just like, we just don't have time.
I told you this.
Here we go, guys.
Yeah, 'cause if you think about it, we wasted like 20 days just to do test.
Here, gentlemen.
That's a long time.
That's a long time to take.
I mean, I don't really care.
So when I'm looking at one like this, this is a lot of this logistic works really nice with population growth, whether it's like bacteria, people, kind of one and the same almost. Bacteria. So what this is telling you is that years after 1950. So year 0 is, you guys are SNRT. What I want to do here is use the logistic regression to find a logistic curve to model the data and superimpose it on a scatter plot. Basically, I want to do L1, L2. All right? I'm going to do L1, L2 as this is my L1 and L2. So let's take a minute and put these in our calculators under your stats. Oh, I have to figure all this out.
Why is it 53?
Why not?
Should we do like 11.4?
No, just do it. You can type it all in. I want to show you how it works. Type them in exactly where you have it. So just start with 0.
I know. I was saying, because normally they do like blah 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 in thousands or in
Yeah, sometimes they do, sometimes they don't.
Jeez, get with the program.
Okay. At this point, you're going to want to change your window, obviously. What's your minimum on your X value should go?
0.
0. And your maximum maybe 60. So my window, I'm going to go 0, 60. My Y minimum, I'm going to start it at 10,000.
And then the Y max is going to be 300,000.
Sure.
Crap.
9. Oh, wait, I forgot to do this.
It's
Oh, sorry, I hit stat plot. Sorry, I hit the wrong button too.
There we go.
It's only supposed to be 6, or 1, 2, 3, 4, 5. No. What?
Why am I missing some?
Why am I missing points?
I definitely.
It's probably not showing the two small ones because their scale is so off. Because this is coming up to 300,000. It might not just be showing it because it's on the screen. That's all. So it's telling you that this is they want you to use that logistic regression. Think of it. It wants you to use that logistic regression because it says use it to see if the data matches it out.
I thought we should have done 11 points.
You changed your table. Your table settings are really off. Your X max should be 50
What's up? Oh.
or 60. And then your Y max should be 30.
How do you say
No, can't have that one. Anyway, so now what I want you to do is I want you guys to go to your stat calculate, and we're doing logistic ones. We have to scroll through and find, it says logist.
8. Or B. It's B.
It's B, yep.
B?
B.
That.
Wow, nice equation.
I pressed enter, but it's not doing anything.
Yeah, it takes a little while for this one to think.
Oh, there we go.
Yeah, this is the one function that it really takes quite a while for it to run the calculation. It's kind of funny, the calculator's like, I don't know if I want to do that. And then it's giving you your A, B's, and C's to put in the function itself. Okay? Just like we've done before, you could then transpose those values into your Y equals to run the table.
Wait, how do you do
How do you
that?
How do you do that? You write them down.
All right.
You guys don't, your calculator, unfortunately, you guys don't have that new operating system that'll allow you to just press a button and it automatically stores it. If you want to do that, there's this thing called the internet and you can download it.
Should we go
Is B the R?
0.10256?
Yes, the B value is your R. Yep,
We
yep,
go
yep,
2
yep.
places past only?
Yeah, just go 2 places past. Round it out to 100 and you'll be close enough on all those, okay?
C is C. B's are A's.
So this means, this would look like this. Y equals 3164, 4, 1, because we're talking about people, over 1 plus A would be 23.58 e to the negative 0.1 x. And that's what I would put in my graph, my Y equals part now,
Okay.
to use the table function to see when it's approaching 300,000 people. And then you'll be able to figure out how many years it would be. Again, it's nothing different than any of the other function stuff that we've done to use your tables to help figure out time frames. It's just a matter of being able to identify that it's logistic versus a cubic. And it's going to be logistic because it's going to start as you look at your graphs or as you look at your tables when you put that in there. It's going to be approaching an asymptote.
And
it's gonna have an
9 is X. Is
16. Yeah, and plus if you're dealing with population, you're never going to have a negative population, so you know it's going to have a ceiling at 0. Okay, so it's one of those deals. All right, that's how you start to pick up on these things. Okay. Ooh, your graphics are much better.
2,000?
Questions? All right, let me give you some of these to try.
What?
So this is 8. Look, we did 2 sections in a row.
In a row.
This is 8.8. It's page 521. All right? Go ahead and do those. 30 through 40 even. It's 3 graphs and 3 solve for x. And then 48 through 51 is 2 word problems that have 2 parts each. They're very, very straightforward. Okay?
Very, very.
He wants to go.
I'm good.